Okay, so here's where we finished off the last day, where we worked out the atomic mass units number, explained why we had decimal values on the periodic table for this. Today we're going to have a look at defining atomic orbitals, looking at energy sublevels, and then there's three rules that determine how these levels are filled, and they are down here. So we're looking at the Pauli exclusion principle, the Aufbau principle, and Hund's rule. And you see them here, the Pauli exclusion principle. No more than two electrons can occupy an orbital. Electrons must have opposite spin, and there's a particular way to denote that. Arrow up, arrow down. For the Aufbau principle, electrons fill the lowest available energy level first. Okay, and I have a diagram to support that. And thirdly, Hund's rule. With orbitals of equal energy, e.g. px, py, pz, electrons fill the orbitals singly first. And before I move to the orbitals, let me just go over one of the triggers in memory aid that I have. The trigger is NAMA. You may be familiar with NAMA. But in any case, what NAMA stands for, it's an acronym for the number of neutrons is equal to the mass number minus the atomic number, which you get number of neutrons, mass number, and atomic number. Okay, so you'll see front and center, there's orbitals listed in front of us. We have the 1s orbital, we have the 2s orbital, and we have an example of a p orbital with the px, py, and pz breakdown of an orbital, of a p orbital. And then we have the other orbital, the d orbital, s, p, d, and f. We don't have a diagram, as it's quite a complicated layout, but in any case we have the sp and d orbitals listed here in front. And an orbital, indeed what an orbital is, it's a region in space around the nucleus. Here's the nucleus in the center, the black dot, and again here the nucleus, and it's a region in space around the nucleus where there is a high probability of finding an electron of a particular energy. And the energy for a 1s orbital is lower than that for a 2s orbital, and gradually as you move out from the nucleus the energy gets higher, and that would be the idea with that. And whereas this is defined as the orbital, the p orbital for example, the px, py, and pz will be defined as sublevels, and that's what they'd be defined as. So you have your orbital, and then you've got your sublevel within the orbital in question. And the same too for the d orbitals. You've got your sublevels that you see over here. Also, you might be interested to know that the s, p, and d and f orbitals have these particular letters denoted to them. S because the orbital is spherical in shape. The p orbital because it's a polar shape, as in you've got poles at either end of the orbital. The d and the f are a lot more complicated, but there's also another explanation to the s, b, d, and f as well, and it has to do with it's got to do with the orbital names S, P, D, and F stand for names given to groups of lines in the spectra of the alkali metals. These line groups are called sharp, principal, diffuse, and fundamental. So these are the line spectra that are emitted when electrons transition from one energy level to another. So you've got your sharp, principal, diffuse, and fundamental, the S, P, D, and F, also from the spectra. In any case, as you step through the periodic table, you notice that the number of electrons increases with the number of protons. For instance, 7, 8, 9 for fluorine, 10 for neon, etc. And we focused on magnesium here, magnesium being atomic number 12, which means that it's got 12 protons, and in a neutral atom it's got 12 electrons. And the electron distribution is governed by the primary energy levels, the main energy levels. Energy level 1 has 2 electrons of the 12. Energy level 2 has 8 electrons out of the 12. and the third energy level has 2 electrons. And if you add all of these up, then you've got 2, 8, and 2, which gives you 12. To the right, you can see then you have the sub-levels. So on the 1s sub-level, we have 2 electrons, which we had from here. Now, when we move into the second energy level, then we have 8 electrons, which we have to complete in the sub-levels. So for the second sub-level, we have the 2s, and we have to obey Hund's rule, the Aufbau rule, and the first one, the Pauli exclusion principle. So we have those 3 rules, the HAP, I call it just for short, and what it means then is that we end up with 2 electrons in the 2s, then we go to the 2p, and we have 2, 2, and 2, and then that would be the 8 then from the second energy level, and then we're left with 2 remaining, and they go into the third energy level starting at the s, 3s, and so you have your final 2 electrons then. And as you continue then through the periodic table, you would continue to move from the 3s to the 3p, and from the 3p to the 4s, and from the 4s to the 4p, and then you have 2 options. Do you go 5s or do you go 3d? Well, 5s has got higher energy level than 3D, which means you have to fill in one of the rules above from HAP says that you've got to fill the lowest energy levels first. So therefore, once you're finished with the 4P, that means you have to go on to the 3D. Then you have to entirely fill the D level before you can move on to the next level, and that's the way that you continue to fill the electrons. You've also got a really important diagram here which highlights that point that I just brought up, because it can be quite tricky to remember the energy diagram that I've highlighted down here. Okay, but if you look at this diagram right here, there's a couple of things that you've got to look at. You've got to look at the consecutive diagonals that I've drawn, say between from here to here, and then going on to the next, the 4s through the 3p, etc. Okay. Now the point about that is that you always compare the consecutive one diagonal after another. Okay. Now what you notice is that 3s, okay, is on this diagonal. If you go to the next diagonal, you'll find that there's no other level that's at the end of that particular diagonal. However, if you go from this diagonal to this diagonal, that isn't the case, because if you go back to this diagonal, the 4s sublevel, okay, has lower energy than the 3d sublevel. Okay, so that means that the 4s has got to be filled before the 3d. And if you do a comparison again, from this diagonal, we have the 5s has lower energy than if we go to this one, the 4d. So that means the 5s has got to be filled before the 4d, etc. Now that's as many as we've got on this diagram. But you can see, if you continue this type of diagonal setup, and it's very straightforward to do, you can make comparisons about what energy level has to be completed before another. And the 4s, again, as I said, is lower on this diagonal than the 3d on the next diagonal, and so therefore you complete the 4s before you complete the 3d. Also take note of the arrow up, arrow down scenario for electrons. You see that for all of these sub-levels that we have, and HAP again accounts for that. Let's make note of that. And yes, from the Pauli exclusion principle, it says here that electrons must have opposite spin, and that comes from the quantum world, and one of the principles of the quantum world, and therefore the electrons must have what's denoted as a spin up or a spin down. They have to be exclusively different from one another. And then you've also got the Aufbau principle and Hund's rule as well. Recall also, for revision purposes, NAMA and HAP and the meanings of those.